In a 120/208 volts three-phase electrical service, feeding a subpanel with only two legs, specifically phases A and B, results in what is technically considered a two-phase panel. The reasoning lies in the source. You are drawing power from two distinct phases of the three-phase system rather than a single phase. While commonly referred to as single phase due to the resulting voltage being similar to standard single-phase circuits, the origin from two phases of a three-phase system defines it as a two-phase configuration. Regarding electromagnetic fields, taking only two of the three hot conductors to a subpanel will indeed create a larger electromagnetic field compared to utilizing all three hot conductors. This phenomenon arises from the distribution of current. When the load is supplied by only two conductors, the current flowing through each of those conductors is necessarily higher than if the same load were distributed across three conductors. A higher current directly translates to a stronger magnetic field. The intensity of a magnetic field is proportional to the current producing it. The interaction of electromagnetic fields is a crucial aspect of electrical system design and safety. Excessive electromagnetic fields can induce currents in nearby conductive materials, potentially leading to heating and energy losses. Furthermore, in sensitive electronic equipment, strong electromagnetic fields can interfere with proper operation. In practical applications, understanding and mitigating electromagnetic field effects is essential. Shielding techniques, such as using grounded metal enclosures, can help to contain electromagnetic fields. Proper conductor spacing and arrangement can also minimize field generation. In three-phase systems, balancing the load across all three phases is a key strategy for reducing electromagnetic field emissions. By ensuring that the current is evenly distributed, the magnetic fields produced by each phase tend to cancel each other out, resulting in a lower overall field strength. When dealing with electrical panels and subpanels, it's important to adhere to the National Electrical Code, or NEC, guidelines. These codes provide standards for wiring, grounding, and overcurrent protection to ensure safety and prevent electrical hazards. For example, NEC Article 310.15 provides guidance on conductor ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. Selecting the appropriate conductor size is crucial for preventing overheating and potential fire hazards. Additionally, NEC Article 250 covers grounding and bonding requirements. Proper grounding is essential for providing a low impedance path for fault currents, which helps to trip circuit breakers or fuses quickly in the event of a ground fault. Bonding ensures that all metallic parts of an electrical system are electrically connected, minimizing the risk of electric shock. In the context of the question, the two-phase subpanel derived from a three-phase system should be wired and protected in accordance with the NEC. This includes using appropriately sized conductors, providing overcurrent protection, and ensuring proper grounding and bonding. When installing a subpanel, it's crucial to consider the load that will be connected to it. The total load should not exceed the ampacity of the conductors feeding the subpanel, and the circuit breakers or fuses should be sized to protect the conductors. It's also important to balance the load across the two phases of the subpanel to minimize voltage imbalances. Voltage imbalance can lead to inefficient operation of electrical equipment and can potentially damage sensitive electronics. In three-phase systems, voltage imbalance is typically caused by unequal loading of the phases. When one phase is significantly more loaded than the others, the voltage on that phase will drop, while the voltage on the other phases will rise. This can create a circulating current that flows through the neutral conductor, leading to increased losses and potential overheating. To minimize voltage imbalance, it's important to distribute the load as evenly as possible across all three phases. This can be achieved by carefully planning the distribution of circuits and equipment, and by using load balancing techniques. In some cases, it may be necessary to use a phase balancing transformer to correct voltage imbalances. Phase balancing transformers are designed to redistribute the load across the phases, ensuring that the voltage is balanced. In addition to voltage imbalance, harmonics can also cause problems in electrical systems. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency. For example, in a 60 Hz system, the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Harmonics are typically generated by nonlinear loads such as electronic devices, variable speed drives, and uninterruptible power supplies. Harmonics can cause a variety of problems, including increased heating of conductors and transformers, voltage distortion, and interference with electronic equipment. To mitigate harmonics, it's important to use harmonic filters. Harmonic filters are designed to block or reduce the amplitude of harmonic currents. There are two main types of harmonic filters: passive filters and active filters. Passive filters are typically composed of inductors and capacitors, and they are tuned to specific harmonic frequencies. Active filters use electronic components to actively cancel out harmonic currents. In conclusion, understanding the characteristics of two-phase subpoles derived from three-phase systems is essential for safe and efficient electrical system design. Considering the impact of conductor selection on electromagnetic fields and adhering to NEC guidelines are crucial for ensuring safety and preventing electrical hazards. When dealing with three-phase systems, it's important to balance the load across all three phases to minimize voltage imbalances and reduce electromagnetic field emissions. Additionally, mitigating harmonics is crucial for preventing problems caused by nonlinear loads. Remember, electrical work should always be performed by qualified professionals who are familiar with the NEC and local electrical codes. Improper wiring or installation can create serious safety hazards and can potentially lead to electrical shock, fire, or equipment damage. If you are unsure about any aspect of electrical system design or installation, it's always best to consult with a qualified electrician. Electrical systems are complex and can be dangerous if not handled properly. Understanding the basic principles of electricity, such as voltage, current, resistance, and power, is essential for working safely with electrical systems. Voltage is the electrical potential difference between 2 points, and it is measured in volts. Current is the flow of electric charge, and it is measured in amps. Resistance is the opposition to the flow of current, and it is measured in ohms. Power is the rate at which electrical energy is transferred, and it is measured in watts. These fundamental concepts are governed by Ohm's law, which states that voltage is equal to current times resistance, or volts equals amps times ohms. Ohm's law is a fundamental principle of electrical engineering and is used to calculate voltage, current, or resistance in a circuit. In addition to Ohm's law, there are other important electrical principles to understand, such as Kirchhoff's laws. Kirchhoff's current law states that the sum of the currents entering a node is equal to the sum of the currents leaving the node. Kirchhoff's voltage law states that the sum of the voltages around a closed loop is equal to zero. These laws are used to analyze complex electrical circuits and to determine the voltage and current at various points in the circuit. Another important concept in electrical engineering is impedance. Impedance is the opposition to the flow of alternating current, and it is measured in ohms. Impedance is similar to resistance, but it also takes into account the effects of capacitance and inductance. Capacitance is the ability of a component to store electrical energy in an electric field, and it is measured in farads. Inductance is the ability of a component to store electrical energy in a magnetic field, and it is measured in henries. Capacitance and inductance can affect the flow of alternating current in a circuit, and they must be taken into account when designing electrical systems. In addition to these basic principles, there are many other aspects of electrical engineering to consider, such as power factor, harmonics, grounding, and overcurrent protection. Power factor is a measure of how efficiently electrical power is being used, and it is important to maintain a high power factor to minimize losses. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency, and they can cause problems in electrical systems if not properly mitigated. Grounding is the process of connecting electrical equipment to the earth, and it is important for safety and for preventing electrical shock. Overcurrent protection is the use of circuit breakers or fuses to protect electrical circuits from overloads and short circuits. By understanding these basic principles and concepts, you can gain a better understanding of electrical systems and how they work. This knowledge can be helpful in a variety of applications, from designing electrical circuits to troubleshooting electrical problems. Remember to always work safely with electricity and to consult with a qualified electrician if you have any questions or concerns. Electrical safety is paramount, and it's essential to take all necessary precautions to prevent accidents.